Before we start with the topic of today's lecture, I have to inform you that I decided to update the Plutus dependency. So in the Cabal project file of week 3, I'm now referencing a different commit hash than in the 2 previous weeks. And I was thinking about that, and of course it would be more convenient for all of us if we could keep the Plutus dependency stable. But I think this is simply not possible because Plutus is evolving very fast, heading towards the Alonso release where Plutus is fully integrated into the Cardano node. So there are lots of changes every week, and if we wait too long and stay on an outdated version, then when we finally have to upgrade in order to use Plutus on the testnet, there will be lots of changes. So I think it's better to do an update at least every 2 weeks or so. So anyway, I've upgraded to this version, and unfortunately that means that some of the code we wrote in the first 2 lectures already won't compile anymore against this new version. But luckily the changes are not that bad. So I thought we'll take the last example we discussed in the previous lecture, the isData example, and just port it to the new Plutus dependency to see what has changed. So I basically just copy pasted the example from last week, the isData example, to this week, now using the new updated Plutus dependency. And the first difference is here in our makeValidator function. In the previous version, the third argument, the context, was called validator context, and this has now changed, and now it is called script context. Luckily, we haven't discussed this context at all in the previous lectures. I just mentioned that it exists and that it is important, but we haven't looked at it in detail, so that's lucky. So this is one change, and another change is that when we construct the actual address, the script address from this validator. Last week we used a capital S script address constructor of address, but the address type has now also changed because it now also allows staking. So it allows a component that of the address referring to a staking address. So the address type has changed and the constructors are different. But there is still a smart constructor with a small s, also called script address. But that takes a validator. I think the capital S constructor from last week took a hash of a validator. So we don't need the validator hash anymore. It still exists and we could compute it, but we don't need it. So once we have the validator, we can immediately apply the smart constructor script address to it to get the address. And I believe that is all the changes we need to make this example compile again. There also have been some changes in the playground. One is a pleasant surprise. I told you earlier that when you copy paste the code that we develop in the Plutus Pioneer program repository into the playground editor, you have to remove the module header. And that seems no longer to be necessary. So we can just copy paste it as is and then immediately compile. Another interesting change is that fees are now considered in the playground. And I'm not sure, I think they are not yet realistic. In all the examples I tried, the fees were always 10 Loveless. So obviously in the real system, the fees will depend on the memory consumption and the execution time, the time it takes to execute the validators. But in any case, because there seems to be a fee in the order of magnitude of 10 Loveless now, it no longer makes sense to have examples with such small numbers. So instead of starting with 10 Loveless initial funds, we should choose a bigger number, for example 1,000. And using that, we can see that the isData still works. So if we, for example, give 700 and then wait, and then wallet 2 grabs with, let's say, the right redeemer with 42, and we wait and evaluate. Then the first transaction, the Genesis transaction, is as before, and we see now wallet 1 and wallet 2 both get 1,000 Loveless in the beginning. And this is the give transaction, and we see that there is now an additional fee output and of 10 Loveless. So 290 Loveless are change, 10 Loveless are fee, and 700 Loveless go to the script. And similar in the grab, which succeeds. So the script, the 700 ADA from the script are consumed, but 10 of those are fees, and wallet 2 only gets 690. When I explained the extended UTXO model in the first lecture, I explained that in order to unlock a script address, the script attached to the address is run, and that script gets 3 pieces of input: the datum, the redeemer, and the context. And in the second lecture, we saw examples of that, and we saw how that actually works in Haskell. We saw the low-level implementation where all 3 arguments, datum, redeemer, and context, are represented by the data type. But I also mentioned that in practice that is not used, and we use instead the typed version, where datum and redeemer can be custom types as long as they implement the isData type class, and where the third argument, the context, is of type script context. It used to be validator context, but this is now changed to script context. And the examples we have seen so far only looked at the datum and the redeemer, but we have always ignored the context. But the context is, of course, very important. So in this lecture, we want to start looking at the context. And this script context type is defined in package Plutus minus ledger minus API, which is a package that until now we haven't needed, but now we do need it, and I also included it in this week's Cabal file. And the context is in module plutus.v1.ledger.contexts. And we see the definition here. So the type script context. And we see it as a record type with 2 fields, one of type txinfo, which is the most interesting one, and then a second field of type script purpose. And the script purpose type is defined in the same module here, and it describes for which purpose the script is run. So the most important purpose for us will be this one, the spending purpose. So this is what we have talked about until now in the context of the extended UTXO model. So this is when a script is run in order to validate spending input for a transaction. But there are 3 other purposes. The second most important one is the minting one. So that comes into play when you want to define native token, and then the purpose of the script will be to describe under which circumstances the native token can be minted or burned. And then there are 2 more purposes, but they are brand new, so I also didn't see them before: rewarding and certifying. So rewarding seems to be related to staking, and certifying to certificates like delegation certificates. But first we will concentrate on the spending purpose. So now the actual context is in this field of type txinfo, which is defined also in the same module here. And this basically it's an abbreviation for transaction info, so it describes the spending transaction. I always said that in the UTXO model that Cardano uses, the context of validation is the spending transaction. So the transaction and its inputs and outputs. And that is expressed in this TX info type. So there are a couple of fields that are basically global to the transaction. And then in particular, we have the list of all the inputs of the transaction and the list of all the outputs of the transaction. And these TX in info and TX out info types again have a variety of fields to drill into each individual input or output. And then we have these global fields, global for the transaction. So we have the fee, then the forge value. So this is if you mint or burn a native token, this will be different from 0. And then this is also new, that was only introduced last week. So a list of certificates and then some staking related info. The slot range, I'll come to that in a minute. So this defines at which time the transaction is valid. Then the list of signatures attached to the transaction. Then basically a map of or a list of key value pairs from datum hash to datum. There was a question raised in the last Q&A session about this. So if I have a transaction output to a script address that carries some datum, I don't really have to include the datum itself. It's also valid to just include the datum hash. But I optionally can attach the datum, and in that case, this will be done in this list. So then I would say which datum belongs to that hash. And finally, we have a transaction ID, which is basically the hash of the transaction, of the whole transaction, including all its inputs and outputs. So there's a lot of information contained in this appropriately named TX info type. But for our first example of how to use this third argument in validation, I want to concentrate on this TX info valid range field. And this brings us to an interesting dilemma. I have stressed several times that one of the big advantages that the Cardano EUTXO model has over something like Ethereum is the fact that validation can happen in the wallet. So as I explained before, transactions can still fail because a transaction can consume an input that when the transaction arrives on the blockchain at the node for validation has already been consumed by somebody else. But in that case, the transaction simply fails without having to pay fees. But what can never happen or should never happen under normal circumstances is that a validation script runs and then fails, because you can always run the script under exactly the same conditions in the wallet already. So you see that it would fail before you ever submit it. And that is very important and a very nice feature. But if you think about it, it's not clear how to manage time in that context. Because time is obviously important, because we want to be able to express validation logic that says that a certain transaction is only valid after a certain time has been reached or before a certain time has been reached. We saw an example of that in the very first example, the auction example, where bids are only allowed until the deadline has been reached, and the close endpoint can only be called after the deadline has passed. And if you think about that, that seems to be a contradiction, because time is obviously flowing. So when you try to validate a transaction that you're constructing in your wallet, the time that you do that in the wallet can of course be different to the time that the transaction arrives at a node for validation. So it's not clear how to bring these two together to, on the one hand, handle time, but on the other hand, guarantee that validation is deterministic, in the sense that if and only if it succeeds in the wallet, it will also succeed in the node. And the way Cardano solves that is by adding this slot range field, this txinfo valid range field to a transaction. And what that specifies, so it's we will look at that type in detail in a moment, but basically it gives a valid time interval. It is a time interval. So it says this transaction is valid between this and that slot. And that is specified in the transaction. And now when a transaction gets sent to the blockchain, submitted to the blockchain, and validated by a node, then before any scripts are run, some general checks are done. For example, that all the inputs are present and that the balances add up and so on, that the fees are included. And one of those checks that happens before validation is that the slot range is checked. So for example, if a transaction specifies it's only valid between slots 10 and 20, then when a node validates this transaction, it checks the current time and checks whether that current time falls into this interval. So if the current time is slot 13, it will be fine. But if the current time is 8 or 30, then the transaction will immediately be rejected without ever running the validation scripts of the script inputs. But that means that if the validation scripts are actually run, then we know that the current time falls into this interval that has been specified there. And that means we are completely deterministic again, because this is just a static piece of data, this slot range. So we can just assume that the current time falls into this interval that is specified there. And this interval is the same when you try to validate a transaction in the wallet or when you submit it to the blockchain and it's validated by a node. That's just part of the transaction, part of the immutable data structure that defines the transaction. So that's how these apparently contradicting requirements of having deterministic validation and being able to reason about time can be reconciled by including this validity interval, this slot range, in the transaction itself. And by default, until now, all the transactions, except the ones in the auction example, but all the other ones, and also normal Daedalus transactions, for example, they always have the full, basically the infinite interval that starts in the beginning of time and lasts until all of eternity. So such a transaction by default is always valid, no matter when it arrives at the node. But we do have the proper possibility to explicitly set a different slot range. And that's what we have to do if we deal with time-critical smart contracts, like in the auction example. So let's look at this slot range type in a bit more detail. So one relevant module is slot. That's in the same package. It's also Plutus minus ledger minus API, but now in module plutus.v1.ledger.slot. And we see that their slot is defined, and slot is just, where is it here? Slot is a simple new type wrapper around an integer. So a slot is just an integer with a new type wrapper around it. In order to construct a value of this type, we can either use the slot constructor, but it's even easier if we look at the implemented type class. We see it also implements the num type class, which means we can simply use numeric literals. So we can write 5 or 17 to define a slot. And now the definition of slot range we see here. And slot range is an interval slot. Now, what is an interval? That is defined in yet another module, also in the same package, also in here in Plutus minus ledger minus API, but now in plutus.v1.ledger.interval. And so that is more general, not necessarily for slots, but we are only concerned about the case where this type variable a is slot, so interval slot. And it's basically defined as something having a lower bound and an upper bound. And then there are some complications because you can also specify whether the bounds are included, whether the lower bound and or the upper bound are included in the interval or excluded. And you also have these special cases that the upper bound is infinity, basically, or the lower bound is the beginning of time. But normally we don't have to deal with these types directly because we have nice helper functions. So I think the most general one is probably the interval one, or one of the most general ones. And this function allows you to give an inclusive lower bound and an inclusive upper bound and construct an interval from that. The documentation, by the way, is wrong there. It claims that the upper bound is not included in the interval, but it actually is. Then we have singleton, which constructs an interval that just contains this one given slot. We have from, which gets the lower bound and then constructs the interval that contains all slots starting at that one slot and then up to the end of time. We have to, which is the opposite. So it gets a slot and contains all the slots starting at the genesis block up to this given slot. There again, the documentation is wrong. It claims that this given one is not included, but it is. Then we have always, which contains all slots from the beginning of time to all of eternity. That, as I mentioned, is the default for transactions if you don't specify anything special. Then the opposite, never, so that's the empty interval that contains no slots. And then we have various functions to work with intervals. So for example, member checks whether a given slot is contained in an interval. Overlaps given two intervals checks whether exists a slot that is contained in both. Intersection computes the intersection of two intervals, which is again an interval. Then hull is the smallest interval that contains the two given intervals. Contains gets two intervals and checks whether the second one is completely contained in the first one. So all slots from the second interval are also in the first interval. And you can check whether a given interval is empty. Finally, you can have before and after. So before given a slot and an interval checks that this given slot is earlier than the beginning of the interval, and after the given slot is later than the end of this interval. So let's play a bit with that in the REPL. So let's fire one up. And let me import the two relevant modules, Plutus v1 ledger slot and interval. So first of all, as I said, there are two ways to define a slot. I can say slot 3, but I could also just say 3. But then I have to tell the compiler that I want a slot if it's not obvious from the context. This uses the aforementioned num instance for slots. So I can use numeric constants. Okay, and for now we saw there are various helper functions to construct intervals. So for example, let's first use the interval function. Let's say we can do something like, for example, interval slot 3, 10. So this now gives us slots 3, 4, 5, 6, 7, 8, 9, 10. So here we see the lower bound is finite, so it's not the beginning of time, it's a specific slot, namely 3. True means that 3 is included. And then for the upper bound, same thing, it's a definite slot, not the end of eternity, namely 10, and it's also included. And we can check for example, the member function, so we can do member 5 interval slot 3, 10. That's true. So 5 is included in this interval. I can also check the bounds. So the 3 is included. 10 should also be included. But 11 is not included. And neither is 2. So now let's use the from constructor. So I have from, for example, slot 20. So we see again the lower bound is a definite slot, namely 20, which is included, and the upper bound is positive infinity. So if I check for membership, so 20 should be included in that one. It is. 19 should not. But everything starting at 20 should be included, no matter how large. So slot 1 million is still included. And finally, let's try the 2. So for example, 2 100. So here we have the opposite situation. So the lower bound is now not a definite slot, but negative infinity. But in practice, of course, that means the genesis slot. Time starts at genesis. And the upper bound is slot 100, which is included. And again, we can do membership checks. So for example, 7 should be a member. And 100 should also be a member. But 101 is not a member anymore. Finally, we can check this contains thing. So for example, contains, let's say, 2 slot 100 interval 30 50. That is true because the interval that contains all slots between 30 and 50 is included in the interval that contains all slots from 0 to 100. But if I change that to, let's say, 110, it's false because this is not completely included. There is an overlap, but for example, 105 is in the second interval, but not in the first one. However, we also have this overlaps function. So this gives true because there is an overlap. But if we change this to start somewhere beyond 100, for example, 101 or 102, then we no longer have an overlap. So this is how you can work with this slot range type. And now that we have discussed this, we can look at an actual example of a contract that now for the first time actually looks at the third argument, the context, and does something interesting with it. One of my colleagues at Input Output bought some Ada for his nephews and nieces. And of course, I don't know any details about that. But just imagine you want to make a gift of Ada to a child. So you want the child to own the Ada, but you only want the child to have access to the Ada when he or she turns 18 or 21 or whatever. And using Plutus, this is very easy to implement a scheme like that, a vesting scheme like that. So I copied the isData contract and into a new module that I called vesting. And as our first example of a validator that actually uses the context, I want to try to implement this vesting idea. So you put money into a script and only the dedicated person can retrieve it, but only once a certain deadline has been reached. So the first step is to think about the types of datum and redeemer. And datum, I think in this case it makes sense to have exactly these two pieces of information, the beneficiary and the deadline. So let's define this type. Let's call it vesting data or datum. And let's make it a record type with two fields. We can call it beneficiary. And so that will be the entity that can actually access the money. So we identify it by his or her public key, or to be more precise, public key hash is more convenient. and then we need this deadline, and that will be a slot. Okay, we change the name. Right. Now what about the redeemer? And in this case, I think we don't need any information in the redeemer, because all the information that we need about the time and about the entity that tries to retrieve the money is contained in the context. So for datum, we can use this new type, vesting datum, but for a redeemer, we can just use unit. Let's call it, I don't know, dat for datum, and this will be just unit, and now we really need the context for the first time. So we need to check two conditions. One, that only the beneficiary has access, can unlock a UTXO sitting at this script address, and that we can check by checking that the beneficiary's signature is included in the transaction. And secondly, the timing. So we must check that this transaction is only executed after the deadline has been reached. And with something as relatively simple as this, we could probably just write that in one go. But I prefer to do it a bit more top-down and use helper functions. So let's start by just writing these two conditions without actually implementing them. And I also like to always give an appropriate error message, which makes it easier to debug. So the first condition is the signature. So if that's false, then maybe an appropriate error message would be beneficiary's signature missing. Okay, and now, as I said, we could do that inline, but let's delegate it to a helper function to make this easier to read. So something like check sig. Okay, and now we need a second condition, and both of those must hold. So we can chain them together with a logical AND, which is a double ampersand in Haskell. Okay, and the second condition is the timing. So if that is not fulfilled, then as error message we can say something like deadline not reached, and then check deadline. Okay, and of course the formatting in Haskell leaves a lot of room to creativity, so maybe you have other preferences how you want to format this. Right, so now let's implement those two things. So we need these two helper functions, check sig, and that will be a Boolean. And then we also need check deadline, which will be a Boolean. So let's look back at the script context type. And we are not interested in the script context purpose. We know that it is spending in this case, because we are writing validation for spending from a script address. So the interesting one is the txinfo. And both the timing information and the signatures are contained in this txinfo. So because we need it for both conditions, it probably makes, and because this field name is quite long, maybe we add a third helper function that just gives us this txinfo. So let's add that here. Info type txinfo. Okay, and that is, what was it, script context txinfo, and we pass in the ctx, the context, our third argument that we haven't used before. Now for the first helper function, the check sig, we must check that the beneficiary has signed the transaction. And in the txinfo value, we have this field, txinfo signatories, which is a list of pub key hashes. So we must check that the beneficiary's pub key hash is included in this list. That means that the beneficiary has signed the transaction. So we can implement this first part now. There's a common Haskell helper function defined in the standard prelude, but also in the Plutus prelude called elem that checks for membership in a list. So we want to check that the pub key hash of the beneficiary is included in this list of signatories. So how do we get the pub key hash of the beneficiary? Well, that's just the beneficiary field of our datum. And in the case of elem, I prefer to write that inline because then it reads more natural. So now the list of beneficiaries, and that is the tx info signatories of our info. Okay, that's the first condition. And now for the check deadline. For that, we need this txinfo valid range field, which gives us a slot range. And we must check that this transaction is submitted only after the deadline has been reached, or when the deadline has been reached. And as I explained before, the way time is handled is that during validation, before any script is run, it is checked that this range that the transaction gives actually includes the current slot. So we know that the current slot is included in the slot range that's given here. And but we don't know exactly what the current slot is because this slot range might be large. It might be an interval that contains many slots. And all we know is that one of those slots is the current time. So in order to make sure that the deadline has been reached, we must check that all the slots in the slot range are after the deadline. And one way to do that is to say that this slot range is included in the interval that starts at the deadline and goes to the end of time. So let's do this. So check deadline. So the interval that starts at the deadline and goes to the current time is from the from that we played with earlier in the REPL. And now we need the deadline slot, and not deadline slot, deadline of our datum. And that contains, and now we need the time interval, the slot range from the transaction. So txinfo valid range of our info field. So again, we don't know what the current time is, but we do know, because we have reached script validation, that the current time falls into this txinfo valid range info field, because that is checked first. If it wouldn't, then we would never reach this point in the code, because then the validator wouldn't even run. So after this first step of validation, we know the current time lies into this range. And now we check that this range is included in the range that starts at the deadline. So other way around with contains, the interval that starts at the deadline contains the valid range, which in turn contains the current slot. So this makes sure that the current slot is indeed included in this, which means it is later than, or not earlier than, the deadline. So that completes the validation logic. Now we must just take care of the boilerplate. So maybe typed is not a good name anymore. Let's call it vesting. Okay, and the types have changed. The datum type is now our vesting datum. And redeemer is just unit. So vesting, vesting. That should be fine, except here we also have vesting datum and units. Okay, now the wallet part I already changed because, like before, I want to concentrate on the validation part in this lecture and talk about wallet in much more detail later. So first of all, what parameters do we need? So the person that wants to make the gift, we need the beneficiary, the deadline, and also the amount. And for this purpose, I created this gift params type that has these three fields. And the grab doesn't need any parameters. And then I just changed the contracts accordingly. So for the giver, I compute the datum that we want to use, which just takes the beneficiary and the deadline from the parameters. And then the constraint in this case is I want to pay to the script with this datum and the specified amount of Loveless. And the rest is as before. I just changed the log message. Grab is a bit more evolved because we have to, the grabber has to find the UTXOs that he or she can actually consume. So this I put into this helper function here. So what this does, it looks at the whole UTXO and then applies this filter to the entries and only keeps those that are available now. And this is the function that filters. It gets the address or the public key hash of the wallet and the current time and the transaction output to consider, and then checks whether that's available. So it first checks that the datum is actually available, the datum hash, and then it tries to deserialize the datum hash, and if that succeeds, then this here is actually the interesting check, line 124. So it checks that the beneficiary of that UTXO is indeed the public key hash of this wallet, and that the deadline doesn't lie in the future. And actually from the wallet we have access to the current time, that's this current slot function, and also to our own public key, which is this own pub key function. And then this is as before, so I say that I want to consume all these script outputs that are now found, that are available, that are for me, and whose deadline doesn't lie in the future. And then I add another constraint, must validate in and give the slot range interval from now. As I explained before, if I don't do this, then by default the transaction will use the always slot range, which means the transaction is always valid. But this won't do in this case, because then in the validation logic we would get this always interval. So we wouldn't know anything about the current slot, and we wouldn't be able to decide that the deadline has been reached. So it's important that here I restrict that and actually use a validity interval from now. I could, of course, also use singleton now, for example. That would also be fine. But then there would be a problem if there's some sort of network delay and the transaction is delayed and only gets their slot or two later, then that wouldn't work anymore. So I think the safest option is to use the interval that starts now and then goes into eternity. Oh yeah, and I also check that if there's no UTXO available, then I don't even try to submit the transaction. I just log a message that nothing is available. So I want to make sure that when I submit that I also get something in return, because otherwise I would have to pay fees for a transaction that doesn't have any outputs. So let's try it out in the playground. I copy pasted the code into the editor. Let's start by again increasing the initial funds to something bigger, like 1000. And now let's have wallet 1 make a gift, and then wallet 2 try to grab it. So give. And now we run into a technical problem that we need the pub key hash of the beneficiary, so of wallet 2. And I think there's no way in the playground to actually get to that pub key hash, which is a bit unfortunate. But if we go to the REPL and we import wallet emulator and also ledger, there's a function in wallet emulator called wallet pub key. It takes a wallet and returns a pub key. And from ledger we have function pub key hash, takes a pub key and converts it into a pub key hash. And finally, what is wallet? We can ask for wallet, and that is just a new type wrapper around an integer. So we can get the pub key hash of wallet 2 by chaining this together. So wallet pub key wallet 2, and can use this. So paste that here. Now I can decide on a deadline, let's say some arbitrary value, slot 15, and an amount, let's say 500 Loveless. Okay, and let's first check the case where it works. So wallet 2 waits long enough. So let's add a wait action until slot 15. And after that, let wallet 2 try grab and add another wait action to give enough time to process the transaction and evaluate. Okay, and we see first transaction as always is the Genesis transaction that distributes the initial funds. Then slot 1 we have the give transaction, so it takes the initial 1000 Loveless UTXO, pays 10 Loveless fee, 490 Loveless change, and deposits the 500 Loveless into our script address. And then in slot 15 the grab is successful, so the only input in this case is are these 500 Loveless, 10 Loveless fee, and wallet 2 gets 490. So wallet 1 ends up with 490, wallet 2 with 1490. Let's also briefly look at the case where the grab happens too early. So let's just change that to slot 14 and reevaluate. And we see there are only 2 transactions. So the give happens, but the grab does not. And we also see the log message, no gifts available, because this is now evaluated at slot 14. So the wallet contract realizes that this UTXO, because of its deadline of slot 15, is not yet available and filters it out. And then there's no UTXO left and the contract doesn't even try to submit a transaction. So that was our first example of a Plutus validation script that makes use of the third argument, the context argument. And I think it's quite a realistic example. So you could actually see this contract in the wild and see it actually be used. Our next topic will be parameterized contracts, but let's start with an observation with the existing one. So I have the existing contract again, same initial condition, but now I want to look at a different scenario where I have 2 gives in the beginning. Wallet 1 gives to wallet 2 and wallet 2 gives to wallet 1, and also at different slots. So I looked up this pub key hash of wallet 1 the same way as I did before in the REPL with pub key hash wallet pub key wallet 1. So these 2 transactions can happen concurrently because they don't depend on each other. But after that, let's add the wait action, and I can just wait until both deadlines have passed. So until slot 25, for example. And now I let both wallets grab. And let's wait for one more slot. and evaluate. Okay, and we see that everything went well. Genesis transaction. Then there are two transactions happening in slot 1. This is the GIF of wallet 2. This is the GIF of wallet 1. And then in slot 25, we have the grab of wallet 2 and the grab of wallet 1. So that's all good and as expected. But now I want to draw your attention to the script address we have here. So this is the GIF of wallet 2, and the script address for the GIF of wallet 2 starts with E78A. And if we look at the GIF of wallet 1, we see we have the same address here. And that is of course not surprising, because both scripts use the same validator. And I explained that the address is computed from the validator by first compiling it to Pluto script and then taking the hash of that script. So both use the same validator, so they get the same compiled Pluto script code and hence the same address. So no surprise here. Just keep that in mind. In our example script, we have put the beneficiary and the deadline into the datum. But there is another choice or other choices. You could also parameterize the whole script on those two pieces of data, the beneficiary and the deadline. So a parameterized script is like a family of scripts. You can instantiate it with different parameters, and then you get different scripts. They all behave the same, but they have these parameters. So I made a copy of our contract in a new Haskell module that I called Wig3 parameterized. And now instead of putting this into the datum, I want to parameterize the script by it. So that means the name vesting datum is no longer appropriate. So let's change that in vesting param. And so we, instead of using vesting datum here, we just use unit datum. So we have no interesting datum and we have no interesting redeemer. But now I add a new argument to this function, the vesting parameter. So the idea is that now make validator is not a constant thing anymore, but it's a function that takes vesting param and then returns a validator tailor-made for this parameter. So don't have to change much in the code, but now the datum is also a unit, and instead I get this parameter. So I just have to update the helper function. So where I earlier accessed the datum, it's now the parameter. And this also changes because now both datum and redeemer type are unit. Now we come to an interesting question: what do we do here? As is, this won't work because now the make validator has the wrong type. Remember, the make validator must be a function that takes 3 arguments and returns a boolean. But now make validator has 4 arguments. And also we won't always get the same instance, so this must now also be a function that takes vesting param as an argument. And I mean, the first idea would be to simply put that p here to partially evaluate make validator by plugging in the p. Then the type would be correct again in here. But the problem is that, as I explained earlier, in template Haskell, this thing inside the quote must be known at compile time, because the way template Haskell works is before the program is run, while it is compiled, this is evaluated. So template Haskell runs at compile time. So everything in these brackets must be statically known at compile time. But the p is not, because this is an argument to the function. So we intend to call this inst function with different values of p at runtime. So the value of p will only be known at runtime, so this can't possibly work. But luckily there's a way around that, because we have something called apply code that takes two Pluto scripts, and assuming that the first one is a function, it applies this function to the second argument, which is also a Pluto script. So in order to make that work, we can write it inline if you want, Plutus tx apply code. So the p here, we must delete it again. And now the p must go here, the argument we want to apply this to. So this thing here, this Plutus tx compile of make validator, is now a Pluto script for a function that takes such a parameter. So now here we must write a Pluto script for that parameter. And then apply code will apply this function to the script for that parameter, and we will get a script of the right type out of that. But that looks as if it doesn't solve the problem, because now again, what do we write here? How do we get the parameter there? We can't use Plutus tx compile and this quote with p, because then that's the same problem. The p is not known at compile time, but only at runtime. And this is where another important class comes in, the so-called lift class. The lift class is defined in package plutus -tx in module plutus-tx.lift.class here, and it only has one function, lift. However, we won't use this function lift directly, but the importance of the class lies in the fact that it allows us to at runtime lift values, Haskell values, into corresponding Pluto script values. So that's exactly what we need to convert our parameter p into code. But as I said, we will never use this lift directly. Instead, we will use another function. This is defined in the same package, but in a different module in plutus-tx.lift, and that's the function lift code. And if we look at the signature, ignore these two first argument type parameters here, we see it takes a Haskell value of type A, provided A is an instance of the lift class, and turns it into a piece of Pluto script code corresponding to the same type. So if we want to use that, we can do Plutus tx lift code and put our p there and close the parenthesis. So again, this make validator now takes an additional argument, so it wouldn't be suitable for the validator function, but we can compile it. So it's now a Pluto script function that takes 4 arguments. Then we use lift code p to turn the Haskell value p into a Pluto script value, and we use plutus-tx apply code to apply this piece of code with 4 arguments to this piece of code. So the result is a piece of code of Pluto script code with 3 arguments, and that is exactly what the validator function expects. Now there's a problem, however, that we need a lift instance for p. Luckily, similar to how we got a lift instance for isData, there's also a template Haskell function that does the same for lift. That's called make lift. It also takes the name of the type as argument, and I see I forgot to change this into param. Now that still won't compile because it expects an additional GHC extension, namely so-called multi-param type classes. Now we have to make another couple of other small modifications, because now we always have this parameter. So inst now takes this additional parameter. So the validator will also now take this additional parameter. So we can't any longer simply apply validator script to instance. We must compose with instance. Same for script address. This now also takes an additional parameter. We can again compose. Changes are also necessary in the wallet part. I did them already. The GIF parameters stay the same, but the endpoints are slightly different because in the grep endpoint earlier we only had unit argument, so basically no argument. Now we need the slot because in order to construct the address that we grab from, we need to have the parameters, and the parameters are the beneficiary and the deadline. The beneficiary will be the wallet itself, so we don't have to pass that in the endpoint. The wallet can find that out by itself, but we do need the deadline. So this is now takes a slot argument. And then there are slight differences. So here we construct in the GIF endpoint, we construct the parameters from the passed in parameter argument to the GIF endpoint. And then whenever we need an instance, for example, then we have to, because it's now a function, pass this parameter p in. And in the grep endpoint, same thing. So now we have this additional slot parameter for deadline. And we can construct the parameters using that and our own public key hash. Then again, if we use something like script address, which is now a function, we have to add this p. And now the nice part with this is that we don't need this helper function, this filter anymore. Earlier we got all the UTXOs sitting at the one script address, and then we had to filter those out that are for us, where we are the beneficiary, and where the deadline has already passed. But now it's much easier because the beneficiary is already specified in this parameterized script now. So if we query the UTXOs now, we only get those that are for us. And we just have to check that now is later than or not earlier than the past and deadline. And then we are guaranteed that all the UTXOs we get are actually ones that we can actually consume now. So the grep function becomes significantly easier this way. And if we copy paste this new contract into the playground editor and compile and set up the same scenario as before. So 1000 Loveless initial funds, and then wallet 1 gives to wallet 2, deadline 15, 500 Loveless. Wallet 2 gives to wallet 1, deadline 20, 500 Loveless. We wait until slot 25. Both wallets grab, where now we need this additional parameter. So now that's a disadvantage of doing it this way. Earlier we could just grab, but now the wallets have to know the deadline of the UTXO they want to grab. So wallet 1 wants to grab the one that wallet 2 gave, so that deadline was 20, so we need the 20 here. And wallet 2 wants to grab the gift from wallet 1, which had a deadline of 15, so we put the 15 there. And now we can evaluate this. And again, it succeeds. So here we have the two gifts again, the gift from wallet 2, the gift from wallet 1, and here the grab from wallet 2 and the grab from wallet 1, and all succeed. But now, remember I showed you earlier with the old version of the contract, the script address was exactly the same in all cases. But now if you look here, this is the GIF of wallet 2, and the script address is 5583A3 something. And here it's a completely different address. And this is now because of the parameters, because now the parameters are basically compiled into the script and therefore also into the script hash and hence the script address. So now for different choices of the parameter, we also get different script addresses. And whether that's a good thing or a bad thing, I think depends on the use case. So in our example, The datum became easier. Now datum and redeemer are both trivial, just unit. And the grep endpoint became easier to implement because we don't have to filter the UTXOs anymore. But on the flip side, we now need this additional parameter. We need to specify the deadline on the grep endpoint in order for the wallet to be able to compute the correct script address and then find the UTXOs to grep. For the first part of this week's homework, I've taken the vesting contract and changed the vesting datum. So I added a second beneficiary. So now we have two and a deadline. And the idea of validation should now be that up till the deadline, beneficiary 1 can grep, and once the deadline has passed, beneficiary 2 can grep. So it's like you make a gift to beneficiary 1, but beneficiary 1 only has time till the deadline to retrieve it. Otherwise, you can get it back if you yourself are beneficiary 2. Of course, it's more general here. So your task is simply to write the correct logic here. Everything else should be complete, and I also modified the give and grep. So the give simply sets the given beneficiary as beneficiary 1 and the wallet itself as beneficiary 2. So the giver can get or can grep back once the deadline has been reached and passed. And grep now filters the UTXOs into two different UTXO sets. One checks that this wallet is beneficiary 1 and that the deadline has not yet passed. And the second checks that this wallet is beneficiary 2 and the deadline has passed. And then it generates transactions accordingly. Could be one or two transactions. So one transaction for the UTXOs in the first group and one transaction for the UTXOs in the second group. I need two different transactions because the validation interval must be different. For the first group, I must use 2 now. I must make sure that the deadline has not yet been reached or has reached but not passed. And for the second group of UTXOs, if I want to grep them, I must use a different validity interval from now. We can see the expected behavior in the playground. So I pasted my solution, my sample solution into the editor and compiled. And let's look at the following scenario. I don't need wallet 3 actually. I thought I would need it. So I only have two wallets again with 1,000 ADA in the beginning. And the beginning, first slot, both wallet 1 and wallet 2 give. And they declare each other as beneficiaries. Wallet 1 uses a deadline of 10, wallet 2 of 5. So what does that mean? So this means until slot 10 has been reached, including slot 10, wallet 2 can grep this gift, and afterwards only wallet 1 can grep it. And here the second give of wallet 2 means up till slot 5, wallet 1 can grep it, and afterwards wallet 2 can grep it. Then I, just as an example, waited until slot 6. So slot 6 means here the deadline has not been reached, so wallet 2 still has the right to grab this gift. But here in the second gift, the deadline has already passed, so wallet 2 also has the right to grab that gift. So when at slot 6 wallet 2 does a grab, it should get both the gifts. We can try that out. And we see that it works as expected. So in slot 1, the two gifts by the two wallets are made. And in slot 6, wallet 2 grabs both gifts. And we see in particular, we see the different validity intervals. So here is the from slot 6 one used, and in the other transaction, the to slot 6. For the second part of the homework, I want you to revisit the vesting, the original vesting once again. And remember, we had two versions of the original one, one with one beneficiary and one deadline. The unparameterized version, where the datum carried both beneficiary and deadline, and then a parameterized version where both beneficiary and deadline were now the parameter and the datum turned into unit. And for this homework, I would like you to do another parameterized version where we split beneficiary and deadline between parameter of the contract and datum. So the signature of the validator, make validator function will be like this. Pub keyhash is the parameter of the contract and slot is the datum. So we split these two pieces of information into parameter and datum. So then you have to implement this. So the logic is the same, but now the data just comes from these two different sources. And then just write this boilerplate. And I adopted the wallet endpoints, the wallet contracts accordingly. So now it's actually nicer again. The grep, or it depends how you look at it, but the grep now again doesn't need a parameter because it gets the beneficiary by just taking its own public key hash. And it does no longer need the deadline in order to construct the address because now the deadline is no longer part of the address because it's no longer part of the parameter. And I had to change the logic a bit, but actually it gets much simpler. So maybe this is actually the right way to do it, to take the beneficiary as a parameter of the contract, but put the deadline into the datum. And if we try this in the playground, so let's look at this scenario. So I have two wallets, and wallet 1 gives twice. To wallet 2, once 400 Loveless, once 300 Loveless, but with different deadlines. So with deadline 10 and deadline 20. So the 400 will be available for wallet 2 after slot 10, and the 300 will be available after slot 20. And then in this simulation, I wait until slot 10 and do a grab for wallet 2. So this should only make this first gift available, not the second, because we are in slot 10, so 20 has not been reached yet. And then I wait until 20 and do another grab. So that should give us that gift. And then wait one more block. And everything works as expected. So this Genesis transaction, the first gift to wallet 2 from wallet 1, the second gift from wallet 1 to wallet 2, the first grab, which gets the one gift that was worth 400 Loveless, and finally in slot 20, the second grab, which gets the other UTXO. So this concludes the third lecture, and we have now looked at validation scripts that actually look at the context. We have looked at the type that defines the context, and we have seen examples of how to use it in the form of this vesting contract, and we have particularly discussed how time-sensitive contracts or validation logic can be written in Plutus. And we have seen how to write parameterized contracts.